Hello and welcome back to another edition of Mr. Walker's Chemistry. Today we're going to be covering reaction types, all right? And there are 5 different types of reactions. We have synthesis reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. Additionally, there is some extra miscellaneous things covered at the end of this video related to bonding and reactions in general. So first, synthesis. Probably the easiest of the reaction types. Essentially, it takes the form of A plus B goes to X, or in the case of these examples, lithium plus iodine goes to two lithium iodides. Um, so if we were to label these, it would be A, B, and X. Okay, same thing here. A, B, X, and so on. Really simple. Basically, two or more elements, okay, combine to form a more complex compound. So you could have A plus B plus C plus D. Oops, that's not a D. Goes to Y. That's still synthesis. You're taking multiple things and adding them up to make one thing. Um, so it's not super hard. Um, First step, of course, identify it. Now, here I say, you must be able to predict ionic products. However, covalent will be given to you. So, for example, let me clear some of these. Um, this is ionic. This is ionic. This is covalent. So we have metal plus nonmetal goes to ionic compound. Metal plus nonmetal goes to ionic compound. Here we have nonmetal plus nonmetal goes to nonmetal, covalent compound. So with these ionic ones, you need to be able to predict what's going to happen. In other words, if I give you barium plus oxygen, okay, you need to be able to predict what will happen. So how do you do that? Well, it's quite simple. You look at the charge. So barium has a plus 2. Each oxygen has a minus 2. So in other words, we're going to be putting one barium with one oxygen. But then I need to balance it. Don't forget to balance it. If you forgot how to balance things, just go back and look at that video. So to balance it, well, I'm going to put a 2 here to get my 2 oxygens, which means I need a 2 there for the barium. Okay, it's as easy as that. Obviously, some of these are not balanced. So, like, this would need to be balanced like that. Okay, this one is balanced, and this one is balanced down here. So, just double check all that. However, so that's for ionic. You can use charges to really easily figure out what's going to happen. With the lithium here, lithium has a plus 1, iodine has a minus 1, so I know that I'm going to be forming an Li, like that. And then it's just a matter of balancing to get it all right. Whereas with covalent here, this could go to CO, it could be CO2, so you have to be careful. It could be one of these two. So that's why I said I'll always give you the product for covalent. Okay, decomposition, also extremely simple. It's the opposite of synthesis. We are taking one thing and breaking it into many. So that's what it says there. A single compound breaks into its component parts or simpler compounds. You will never have to predict the products for these, simply because, well, it's hard to predict. Normally, you just have to do the reaction and then find out what actually occurred under given environmental conditions. So this would be like in a lab. You would take some compound and heat it up or cool it down or, put it under different pressure to see what it actually breaks into. So don't worry about it. Just make sure you can identify it. So here we have one big thing breaking into multiple small things. Okay, and once again, you can have A, X, Y, something like that goes to A plus X plus Y, as long as you're just breaking down into simpler things. Okay, single either displacement or replacement reactions, you can say it either way. This is where one thing replaces another in a reaction. So here's our forms here. A plus B, okay, so this would be A plus BX goes to something else, which in this case is AX plus B. And you can see I forgot the calcium here. Okay. Um, that's it. You could see what happened. What happened? Why it's called a replacement reaction is the lithium replaced the calcium on the chlorine. So that's all it is. One thing is replacing another in this whole reaction. All right. Same thing on the next one. You know, it's 2 aluminum plus 3 COF2. And what's happening is the aluminum is replacing the cobalt. So that was really easy. Okay. And you can see on my notes over there, it says a more active element takes the place of a less active element in a compound. This refers to the activity series of metals, which is later on in the video. Generally, you will have that or you can find it. It is not something to be memorized. And it's what it is that metals have different levels of reactivity. So just based on these reactions here, I can know that lithium is more reactive than calcium. Aluminum is more reactive than cobalt. Okay. And this goes back to doing the periodic table stuff when I said, you know, when we look at group 1 and 2 metals, they are very reactive. And the higher you go up on the list, the more reactive they tend to be. So just be careful. Look at the list, okay? And I'll show that to you. And again, you need to be able to predict the products. These are so simple where, you know, A is replacing B in this example, or Y is replacing X in this example. You can go either way, and that can happen. Most generally, you will see this. Okay, that's what almost all these examples down here are, where this is replacing this. Okay. Now, for double replacement reactions, you're switching both A and B. Okay, or both X and Y. It's instead of like here we were replacing one element with another, down here we're replacing both elements. They're both swapping places. So, you know, when we look here, okay, the aluminum and the potassium are swapping places. So now the potassium is bonding to the chlorine and the aluminum is bonding to the phosphate. Same thing down here, okay? Your metals generally switch places, and you can see these are all occurring between ionic compounds in both examples. Okay, this is an ionic compound, this is an ionic compound, this is an ionic compound. All of these are ionic compounds. So as you can see, it says it occurs between ions in aqueous solution. What does that mean? What it means is if I have a beaker, okay, and we've got some water there, and let's take this first reaction. I'm going to take some potassium phosphate, okay, and put it in the water. Because it's ionic, it's going to break up into potassium and phosphate. Okay, these are like separate ions now floating around. And I'm also going to take some aluminum chloride and throw it in there also, and then it breaks down into the aluminum and chlorine ions. And so all these are floating around in space in there. And what happens is that these guys match up and these guys match up because they are more attracted to each other based on their charges. They better balance each other essentially, you know, because potassium is a +1, chlorine is a -1, so they balance each other. Aluminum is a +3, phosphate is a -3, so they balance each other, and then it's done. It's easy, you know, it's simple. And to get these back out, you would heat it up. Okay, so you would add heat, to it and boil all the water off. And once all the water's gone, then you get these two salts on the bottom, and you can use those for different things. So it's just one way that we make some new chemicals is we'll take existing chemicals and recombine them to make more stable chemicals. So again, you should be able to predict this just simply because you're taking the first thing and switching it with the first thing on the second. That's all it is. All right, so take a look at these again. Make sure you understand it. This is replacing this. Okay, this replacing this. That's all that's happening there. And double replacement is even easier because you're just switching the metals, the cations. Okay. Finally, combustion reactions. Simple. Hydrocarbon goes to plus oxygen goes to CO2 and water. This is this is what happens in an internal combustion engine. That's why it's called an internal combustion engine. You're doing a combustion reaction internally. And what powers most cars these days. So hydrocarbon, what is a hydrocarbon? Hydrocarbon is exactly what it sounds like. It is hydrogen and carbon combined together in different arrangements. So for example, methane, hydrogen and carbon arranged like this. Ethane is hydrogen and carbon arranged like this, and propane is like this. Okay, these are propane grills, and we use octane in cars. Octane is C8. Okay, and then the H's that would follow along. So methane plus oxygen, which is the O2. So this is methane plus the oxygen goes to CO2 and water. Just remember to balance it. Okay, always balance out your reaction. Okay, so to ethane plus oxygen goes, it's balanced. So you should be able to predict these because your products are always the same, always these. Okay, CO2 and water, always your products. Okay, that's it. So it's really simple. So now some miscellaneous reactions, things that you need to be aware of, but don't necessarily need to understand so much, I guess. First, the activity series of metals. This is what I was talking about with single replacement and double replacement. It goes from least reactive to most reactive. So least reactive, most reactive. As it says on this slide right here, do not memorize this. It is way too much to memorize. Okay. These are all metals, you'll notice, except hydrogen is bolded because hydrogen is kind of in between. And look, okay, here's an easy way to think about this. Gold and silver. We use these in jewelry. Okay, why do you think we use gold and silver in jewelry? And remember, we're going least to most reactive. Well, it's quite simple. Gold and silver don't react with anything, so they won't tarnish. They'll always be generally shiny. You won't have to worry about cleaning. You go and you clean your house and you use some chemical, you won't have to wear gloves. You can keep your nice fancy gold rings on and not worry about it reacting. Gold and silver just don't react with anything, so we don't worry about them reacting with anything. Whereas you can see, the ones that are on the left side of the periodic table, those alkali metals, okay, lithium, rubidium, cesium, barium, all these are kind of group 1, group 2 alkali earth metals, extremely reactive, okay? They react with a lot of stuff. So we're not going to be making jewelry out of things like calcium anytime soon because calcium, it would just dissolve right off of your hand, okay? Not the best to make jewelry out of, okay? So there you go. You guys hopefully, there's a lab called the Copper Cycle Lab where you're going to be using copper, okay, copper and aluminum. So if I were to write out a reaction like something like this, okay. It's a single replacement reaction because we just have AX plus B. All right, and so we need to go to and figure out what's going to happen. Well, again, predict it. is aluminum actually going to replace copper? Will this happen? Well, let's look at our list. Okay, will aluminum replace copper? All right. Yes, aluminum is higher on the list. Aluminum is higher on the list, so aluminum will replace copper. In fact, aluminum will replace anything that's below it on the list. So lithium replaces everything, gold replaces nothing. So yes, this will happen. So remember, single replacement. So this guy is going to go over there and steal it. So we end up with aluminum, nitrate, and copper. Always remember to balance it out. So nitrate has a -2 charge, aluminum has a +3. Crisscross it. So we get 2 and 3. Okay, so we need to balance it. So we go do that. And then we need 3 of those. So we go with that and that. Okay. So just be careful there. Make sure you always can balance everything out. That's your first miscellaneous thing, and that applies to single and double replacement, where anything up here will replace anything down here. Okay. So here it is in writing, in case you need to write it down. Only thing you need to know, metals above others will replace those below them in single and double replacement reactions. The higher up on the list, the more reactive, so the more likely it is to replace them. So, in your lab, why did aluminum replace copper? Well, I just wrote it out for you and explained it, so hopefully you were paying attention. All right, precipitation chart. This is a chart that is used by chemists to quickly determine if a precipitate will form. Well, what the heck is a precipitate? A precipitate is it's something that settles out. For example, if I have my beaker and it's full of water, and I add chemical A into here, and then I put chemical B into here, they will break up. So let's do AX and BY. Okay, so they're going to break up into A and X and B and Y. Okay, these are all separate ions floating around in space. And A will match up with Y and X will go to B. And so I'll end up with some BX and some AY at the end. Well, will those continue to stay in solution? Or will they settle out? So like, will they form little globules and start to settle to the bottom like sand? And the precipitate is the sand. What I would recommend that you do is pause this video, go back into YouTube or whatever, in another window or tab of your browser, and search for a precipitation reaction. Okay, precipitation reaction, and just so you can see what I mean. Okay, and they might even explain it if it's a good video. Unfortunately, I don't have a good video of it, so I can't show you. So let's look at the table. Your table, which is in your packet that you have, that I gave you, that hopefully you have with the periodic table, and a whole bunch of other things in it, has what's in it called a precipitate chart. So it does not cover all the rules. For example, the reaction 3 of your copper cycle lab is not on your chart. Okay, but copper hydroxide and copper oxide are both insoluble, so that's why you start to see the black precipitate settle out. All right, so let's learn how to use it. Unfortunately, we can't do that. So, all right, so other parts of equation. If you see an S, that means solid. If you see an L, it means liquid. If you see G, that means gas. AQ means aqueous, which means dissolved in water. So if we look at this example here, I have liquid potassium chlorate. I have solid sugar, okay, C6H12O6. I have gaseous water, gaseous CO2, and solid potassium chlorate. When you see something that goes from a liquid to a solid, that means you formed a precipitate. And finally, we've covered this already, but all diatomic gases, okay, which are oxygen, nitrogen, hydrogen, fluorine, iodine, and bromine. Okay, the only thing is bromine is a liquid at room temperature. So just say reaction. Okay, if you see only oxygen reaction, assume O2. Same goes for all the others. We've kind of covered that already. So that's your miscellaneous stuff. Most importantly is this one, the activity series. You may wish to jot this down in case whoever's teaching you doesn't give it to you. But you could also find this online in many different places and just copy and paste it into your notes or something, or print it out yourself. But this will help you see what will replace something else in a reaction or in a lab, and it helps chemists predict whether something will actually react or not. All right. So main focus here is these different types of reactions. Be sure you can identify them, take elements, practice with them, see what you can do. All right. And your textbook is a good resource. Hopefully this will help you understand what's in your textbook a little bit more though. All right, so that's it for today. I hope you learned something. I hope this was helpful, and I'll see you next time.